This is chapter 16, section 2, disruption of genetic equilibrium. Evolution is the change in a population's genetic material over generations. That is, a change in the population's allele frequencies or genotype frequencies. Any violations of the 5 conditions necessary for Hardy-Weinberg equilibrium can result in evolution. So the last part of the previous video, I talked about Hardy-Weinberg genetic equilibrium and the 5 conditions that are necessary for an unchanging population. Just to review the 5 conditions necessary for genetic equilibrium, that is no net mutations, individuals don't leave or enter the population is infinitely large, individuals mate randomly, and selection does not occur. So if all 5 of these conditions are met, then we can say the population is in genetic equilibrium. That means that the population is not evolving and the allele and genotype phenotype frequencies are constant. So this is going to look at the reality of how all 5 of these rules are actually violated in the real world. So the first requirement is no net mutation. But mutations happen all the time at a low rate under normal conditions. But if an organism is exposed to a mutagen is anything that causes a mutation, the mutation rate can increase. Examples of mutagens are carcinogens. These are any kind of substance that increases the risk of cancer, like nicotine in tobacco, ultraviolet radiation. Those are the 2 I can think of off the top of my head. And of course nothing. I don't know. I just completely drew a blank. Anyway, mutations can produce totally new alleles for a trait. Now, it's important to remember that the majority of our DNA is not used at all. So if a mutation occurs in a portion of the DNA that's never transcribed, if you remember transcription and translation, transcription is making RNA from DNA and translation is making proteins from RNA. If there's a mutation in the non-transcribable portion of DNA, then it will have 0 effect. And that mutation can be passed on depending on if it's recessive or dominant. So we're combining a lot of previously learned ideas when we look at this, because you have to remember transcription, translation. You also have to remember how things are passed from parents to offspring, and with the genetics that we studied in chapter 9 with dominant recessive. So most mutagens are harmful because change, as far as DNA is concerned, change is not good. But if the mutation occurs in a dominant gene, most likely, if that organism even is viable as a fetus and it survives fetal development and is born, then most likely the mutation, because it's dominant, is going to show in the phenotype, which means that it will be selected out by natural selection. The problem is if the mutation is in a recessive allele, it's going to be harder to get rid of because it won't always express itself, right? So remember dominant and recessive alleles. For dominant alleles, they are going to physically show up in the population. So if you say, for example, you have a mutation that affects, let's say, a deer population, and this mutation somehow causes a deer to be born with 3 legs instead of 4. Maybe there's a problem with the homeobox. If you remember, the homeobox is the blueprint for where body parts go. It's a sequence of genes that determine where body parts go. So if there's a mutation there, let's say it's, like I said, it's dominant in a deer population and deer are born with 3, not 4 legs, that shows up in the population. That deer will not be able to outrun predators as much as the deer with 4 legs. So like I said, if it's dominant, it will probably be selected out by natural selection through predation or starvation or competition, or even just with selecting mates, which I'll talk about later in this video. But either way, if it shows up physically, then it can get out of the population quicker. If it's recessive, it won't show up in the phenotype as much, so it'll be harder to get rid of. Rule number 2 is that the population remains constant. Nobody comes in, nobody goes out. And of course, we know, I'm a perfect example of this, is that that doesn't always happen. So immigration is the movement of individuals into a population, and emigration is the movement of individuals out of a population. This creates something called gene flow. When you have, remember our gene pool? And you can use a swimming pool as an example of a gene pool. If you have somebody that gets out of the pool, their genes are taken out of the gene pool, so their DNA and their alleles are no longer available for the next generation. But if you have new individuals jumping into the pool, all of their alleles, all of their genetic information is now available for the next generation. This creates gene flow, genes moving from one population to another. So I effectively took my genes out of the American gene pool and I dumped them into the Thai gene pool. This is just a GIF that shows you just how much immigration and emigration is happening on a daily basis. It's a lot, yeah? So obviously rule number 2 is like seriously broke. Right, the third requirement is an infinitely large population. Since equilibrium is based on probability, the laws are not the same for medium and small populations. And especially when you look at gene flow and mutations, you get something called genetic drift. So genetic drift is a phenomenon by which allele frequencies in a population change as a result of random events or chance. Now, the problem is when you're comparing a large, medium, and small population. If you have allele frequencies change in a small population, it's going to have a bigger effect on the population as a whole rather than a large population. So large populations can withstand gene flow and genetic drift more than small populations can. So for a small population, the failure of just one individual to reproduce can greatly affect allele frequency. A good example is just imagining severely endangered species like the koala or the panda bear, right? So pandas are so endangered that we actually ship pandas from country to country to try to mate with other pandas in zoos. Just to try to make sure that the gene pool doesn't shrink to like 2 individuals, because the smaller your gene pool is, the fewer genes you have to choose from for the next generation. And one thing that is very true, that if you have a small gene pool, you have a higher chance of abnormalities and mutations that occur because there's just not enough variety in the genes available. Oop, sorry, that was a little animation I wanted to show. So you've got the second generation. This is based on the number of individuals that can reproduce. You started off with, I think, 6 each or 8 each. And now for the second generation, you have, yeah, so you can compare. You got more blue than red. And so with the third generation, you can see that the number of red balls or red individuals is being reduced quite significantly, so that even by the 4th or the 5th generation, you just don't have any red individuals left at all. And that's the danger of a small population. A little change for a small population has a huge effect. And that is a big reason why it's important for us to try to protect endangered species, especially endangered species that are in the wild still. There's different categories of endangerment. There's endangered in the wild, and there's some that are endangered. They don't exist in the wild anymore, and they're only exist in captivity. I'll do an activity about that a little bit later on. But the main point is that the smaller your population is, the more effect a small genetic change has.
So here's a question for you. Have you ever compared the candy you get on Halloween with your friends? My sister and I, a bit competitive in the sport of Halloween candy hunting, we both had preferences of which kind of candy we hoped to get in our buckets each year. And as for me, I love gummy bears. And every once in a while, someone would have them mixed in a big bucket. And I remember watching with intense focus the hand that picked out the candy, hoping for gummy bears. Getting those gummy bears was always total luck, total chance. Well, unless, of course, the entire bucket they had was actually gummy bears, but that would not be luck. That would be pure bliss. But that's never happened to me yet. So why bring this up? Well, what if instead of candy, we were talking about insects? And they weren't in a Halloween bucket because that'd be kind of gross. They're on the sidewalk. And when you're scooter riding through the neighborhood on Halloween to collect candy because scooters may or may not be our super awesome childhood mode of transportation, you squash some. Accidentally, of course, because you like insects overall. Were the ones that survived better adapted? Did they have some special ability to foresee events or to move your scooter away from them? Well, assuming they were all just there on the sidewalk in the path of your trick or treating, then no. In this random event example, the survivors were not better adapted. They were lucky. It was chance. And the ones that were squashed were, in this case, at the wrong place at the wrong time. And that's what genetic drift is. Genetic drift can change allele frequencies in a population. Remember, alleles are a form of a gene, but genetic drift is random, unlike natural selection. Recall that in our natural selection video, organisms that have traits that result in high fitness are able to pass those alleles on to their offspring. This is where that survival of the fittest comes into play, but not genetic drift. With genetic drift, the organisms aren't necessarily more fit, they just have won the game of chance. So let's look at a representation of genetic drift known as the bottleneck effect. I always like to remember this one by focusing on the word bottle. Well, let's say that we have a bottle here and we fill it with our Halloween candy. If we shake it out and we only get a few of the candy pieces, does it necessarily represent the whole bottle as far as the candy frequencies you got out? Nope. In fact, one of the types of candy pieces isn't even there. That type is totally eliminated. We'll consider a natural disaster, such as a forest fire. The surviving organisms weren't better adapted. They were likely just in an area where they weren't directly affected. But the survivors don't happen to represent the original population, so there's definitely going to be a new allele frequency among the surviving population. Bottleneck effect. Another time to see genetic drift is when you're talking about the founder effect. In this case, you may have organisms that have founded an island or some new area. The few organisms that arrive to start a new population do not necessarily represent the original population that they came from. Let's take a case where maybe some seeds that are dispersed by wind end up in a new area that happened to be one that was ideal for their growth. This new population grows. Well, those seeds that landed in this new area may not necessarily represent the original population of plants from which they came from. It's a random sample, founder effect. In summary, genetic drift can make some big changes to allele frequencies, and it's a mechanism for evolution. So, one last thing. Which type of population do you think would be more vulnerable to genetic drift? A big population or a small population? If someone is just doing some intense candy hunting and by accident scooter rides over a few insects, look at the results in the small population versus the big population. As you can see, this random event has the potential to cause more change from the original in the small population. See, there weren't as many representatives there in the first place. So, in many incidences of genetic drift in populations, the impact on small populations is especially significant. Well, that's it for the Amoeba Sisters, and we remind you to stay curious.
Okay, so the major point there is that genetic drift is much different from natural selection because it's completely random, and it is not necessarily a result of fitness or adaptation or anything like that. It just happens to be just random events that occur. So this chart is in your books somewhere. I don't know what page it's on, but this is a really good graph of how genetic drift affects different size of populations. So the green line, we have a population of 25, red is 200, and blue is 2000. And you can see over 150 generations what genetic drift effect can have. So even on a population of 200, you can see at different times that there were certain events that had huge uh, effects on the population, but it was able to recover. But whereas the small population, with whatever this event was, it just could not recover and it went extinct. And for the blue population, it was large enough that the genetic drift, or these things that occurred, were not significant enough to affect the entire species overall. Okay, rule number 4 was that matings occur randomly, but many species, including humans, don't mate randomly. It's influenced by distance, physical characteristics, etc. Assortative mating is a selection of mate based on a similarity of characteristics. And then the 5th requirement is an absence of natural selection. Of course, we know that natural selection is an ongoing process in nature. It is the single most significant factor in disrupting genetic equilibrium. And there are 4 types of selection, and one of them is going to link back to the non-random mating. That's why I just kind of briefly described non-random mating, because I'm going to address it again next. So the 4 types of natural selection are stabilizing, directional, disruptive, and sexual. And the sexual selection will be the one that relates back to the 4th requirement of random mating.